This is a PNP emitter follower practice problem. So we can see here we have the current gain, the voltage source, the R1 and R2, and I'll draw those in a minute, and the emitter resistor, RE. And we also see that we have a time-varying input signal that will add into the base, and that has an amplitude of 150 millivolts at 5 kilohertz. So it says here the resistor network R1 and R2 will provide the DC voltage at the base. So what I'm going to do is just draw that in here. So I'm going to go over, let's see, and this is going to be my, let's see where, R1 is 33K and R2 is 10K. Okay, and we've got our RE is equal to 1K here, and this is 12 volts. Okay, so the first thing we can do is figure out our base voltage because we have this resistor network that's creating the voltage drop, or creating the voltage divider that gives us the voltage at the point in between the resistors that goes into the base. So we know that our VB then, that spot right there, is going to be equal to V at the V of the supply, Vs, times R2 over R1 plus R2. And what I'm going to do is I'm going to use Matlab, just because I've been using Matlab quite a bit. So if I say my, let's see, I need to go back. I have this set up. I can do this. And then minimize this. Yeah. So I can say R1 is equal to 33,000. R2 is equal to 10,000. Beta is equal to 90. RE is equal to 1K. I think that's it. So, oh, and my source voltage. So Vs is equal to 12 volts. Now, if I want to calculate VB, I can just write in the equation. So I can say Vs times R2 divided by R1 plus R2. And I get 2.7. Great, so that's the first thing. So let's, I can insert a table in here. Yeah, so insert a table. So I'm going to add this table in over here. So let's see if I put that kind of down at the bottom. Or I'll put it in the voltage gain part. Right, and I'm going to say this is VB, VE, VC, V. This is going to be EC because I'm going from the emitter to the collector, and then I, E, IB, and IC. Okay, so right now I've got 2.8 volts. And so now if I want to calculate VE, if I look at my circuit again, I'm right here. So let's see if I go back to draw. So I know what my voltage is at VB right here. I think I need to use my pen again. Right, so I know what my voltage is right here, and so I need to add 0.6 volts to get up to my VE right there. So I'm going to do VE is equal to VB plus 0.6, and I get 3.4 about, so I'll just type in 3.4. Okay, and then if I look at my circuit here, my VC, which is, let's see, right here, this is going to be VC. I can see that it's connected to ground right here. And so since it's connected to ground, then I know that this is equal to 0. And then that helps me to figure out my VEC. So if my VE is at 3.4 volts here, 3.4 volts, right, minus 0 gives me 3.4 volts. So there, I've got all of my voltages right now. So if I want to figure out what my IE is, that's the next step. What I can do is I can look at the voltage drop across my RE. And so for the voltage drop across my RE, I need the voltage drop is going to be the voltage from the top to the bottom. So I know my VS is 12, and I know that my VE here is 3.4. So what I'm going to do is I'm going to say that VE is equal to 12 volts, or let's do, is equal to VS minus VE. And this would be, instead of VE, I'm going to call this V across RE. So that's the voltage drop across RE right here. So I can figure that out. So I can say V, call it RE is equal to VS minus VE. And I get 8.6. So that means that the voltage drop across here, because this is at 12, VS is at 12, and VE is at 3.4, then there's a big voltage drop across RE. So what I can do then is to calculate IE, right? I can say IE is equal to V of RE divided by RE. And so that'll give me, I'm just using Ohm's law there, right? So that's going to give me 0.0086. So for all of the currents, I'm going to write these in milliamps. So milliamps. And so looking at my current over here, this is going to be 8.6 milliamps. Okay, and so what I'm going to do now is I know that because my IE is equal to my IB plus IC. And where does that come from? Well, looking over here, thinking about this, if I were to draw, if this is my V and this is my E, so this is E, right? And from E, I'm going to here, right? There's a diode here, and I go to B, so this is B, right? And I'm also going this way down to C, So IE, I'm getting IE is this way, and it splits this way and this way. And so therefore, I'm going to say IE is equal to IB plus IC. And then I'm also going to use the equation that IC is equal to beta times IB. And I'm going to plug this into this equation right there. So I get IE is equal to IB plus beta IB. And if I factor out my IB, 1 plus beta, then I can solve for IE. And I get IB is equal to IE over 1 plus beta. And I can calculate that over here in Matlab. So IB is equal to IE divided by 1 plus beta. Oops, yep, it corrected it for me. Okay, so in IB I get 9.5. So that's 95. That's 0.95 milliamps. So this is going to be 0.95 milliamps. Sorry, that's not right. I want to say 0.095 milliamps. So it's 95 microamps. And now remember too, now I can use this equation again. Going back, and I'm going to use this equation to calculate my ICs because I have beta and I have my IB. So I'm going to say then that over here in my Matlab, I'm going to say IC is equal to beta times IB. And I get 0.0085, and so that's 8.5. Back to black. 8.5 milliamps. So I have all of my voltages now. If I look over here, I've completed, I haven't done the graph yet, but I've completed this step. So let's think about the graph. So if I draw my graph, I'm gonna have something that looks like this, right? This is my VCE down here, or VEC, let's call it, because remember I'm going from, my current flows from E to C with a PNP transistor. This is gonna be my IC, and we're gonna record this in milliamps. We're gonna record this in volts, right? And how I'm figuring out the load line first. That's the first thing I wanna do. So I know for the load line, I need to think about cutoff and saturation. So if I have cutoff, that means for this is my, this is my voltage, and then I have my resistor, RE. This is my E. This is my RE. This is my C. And then that's connected to ground. And remember here, for this, in this case, I don't have the C and the E connected. It's open. And so when I measure the voltage at E, because no current can flow, there's going to be no current drop or voltage drop across RE. So this has to be at VS, which is equal to 12 volts. So the voltage at E in cutoff has to be 12 volts. And then my voltage at C has to be 0 because it's connected to ground. So that means that my max VEC is going to be the difference. So VE is 12 and VC is 0. So that's going to give me 12. So this is 12 volts, right? And then if I want to figure out my maximum collector current, so I'm going to have my V and then my RE. This is the emitter, right? And there's a wire now. That wire is there. That's connected to ground. So now if I were to take a probe and measure the voltage at E, I would get 0. So the voltage at E is 0, right? And the voltage at C is 0. So what that means is I can calculate the current that goes through here just by taking the supply voltage, Vs, and dividing it by Re. So I'm going to have I for the collector, just for this case, just for when we're in saturation, so we can define our load line, is equal to Vs over Re. So I can type that in over here. So I'm going to call this a different IC. I'm going to call it IC in saturation is equal to Vs divided by Re. And I get 0.012. And so what that is then over here, that is going to be 12 milliamps. And what I do then is I take a line and I just draw it like that. Oops, that really wasn't good. Do this better. There we go. And now if I want to put in my where I'm operating, then I can go back to my table and I can find my VCE is 3.4. So let's say that's right around here. I'm going to say that's 3.4. That's my actual operating position, location on the voltage drop across VEC. And then my IC is 8.5. So that's right about here. So it's going to be 8.5. And if I find where these intersect, that's where I'm going to be operating. So my characteristic curve has to go through there. So I would draw something like this, right? And so then I'm going to label this as IB is equal to 95 microamps. So there, I've drawn in my characteristic curve. I've drawn in my load line. Where on the load line is the current operating. So pretty far back here. I probably want it right on the load line. So let's see if I can fix this a little bit. So let's say that move my position just a little bit. So we're going to say we're operating like right here on the load line. and then we'll get that. So there's my IB is equal to 95 microamps. Okay, so we've got that, we've completed that. And what is the voltage gain of the circuit? So looking at the circuit, this is an obvious emitter follower, and it's called an emitter follower. And so what that means is that the output is right here on the circuit. So that's going to be my out, V out. And remember that the function of an emitter follower is just to buffer the input signal between the two circuits that I'm trying to connect to. So my voltage gain for an emitter follower is just 1. And what does that mean, really? It has a lot more to do with my time-varying input signal. So if I have a time-varying input signal of 150 millivolts, I'm going to have something that looks like this. This is my input signal. This is time. This is right here is 150 millivolts. That's my amplitude, right? And what happens when I add this to the bias voltage on the base, then I get something. So this right now, this is my 0 here. When I add it to the bias, I am just bringing it up to my value for VE is 3.4. So now I'm just taking the same signal and I'm biasing it up to 3.4. And I'll have the same signal. This is time. And so the amplitude here, so let's make that a different color. The amplitude from here to here, this is still 150 millivolts. And then on the output, I'm going to have, I'm sorry, so this is actually the output. So this is my output. Let's look at the input. So the input is on the base, right? So the input is going to be, if I look at my base, that's going to be at 2.8 volts. So this is going to be at 2.8 volts. And this is time, and I'm going to have the same signal here. So here, from here to here, this is still 150 millivolts. So the amplitude of my wave. So all I've done with this circuit is I have taken an input signal here, this input signal. It's centered around 0, and I've biased it up here to put it on the base. So this, let's see if I can erase this. So I've biased it on base in this case, and then this is my output right here. So this is my output right here, and so this is what comes out of this spot right here. That's the signal that comes out right here.